The fact is, if you look at the way that molecules are actually hooked up, for instance, let's look at a water molecule here. Ideally, there should be no charge on this molecule, and in fact, there is no net charge. But the truth of the matter is, if one wants to get frank, that oxygen molecules, and we always are here, that oxygen molecules have a greater affinity for electrons than do hydrogen atoms, i.e. they're electronegative. And therefore, what this means is that the swarms of electrons that are holding all this together, the orbitals, are drawn more closely to the oxygen, and the hydrogen atoms, i.e. the protons, are relatively willing to give up their electrons. And what this means is that there's an unequal distribution, and as a consequence, there's a fraction of a negative charge here at this end of the molecule, and there are fractions of positive charges here, because it's not as if they've totally given up the electrons, but the electrons are shifted more in this direction. And this molecule is therefore called a polar molecule by virtue of the fact that here it has a positive pole, and here it has a negative pole. There are other pairs of molecules which are relatively equally electronegative. For example, here if we have a carbon and a hydrogen, these two atoms are roughly equally matched in terms of their ability to pull electrons away one from the other, and as a consequence there is no net shifting of charge. And keep in mind that this delta I show here is only a fraction of an electronic charge. It's not the entire electronic charge moved over. But this has important consequences for the entire biochemistry that we're about to get into, both today and on Monday. Important because polar molecules, such as water like this, are able to dissolve certain compounds, and nonpolar molecules, which have large arrays of these kinds of bonds, or carbon-carbon bonds, these are relatively insoluble in water, and that has important consequences for the organization of biological membranes. We might have a carbonyl bond here, that is a C going to an O via a double bond, and here we have once again a situation where the oxygen is far more avid in terms of its willingness and interest in pulling electrons toward itself, and therefore the carbon gives up a little bit of the electron cloud and it becomes slightly electropositive, whereas the oxygen atom becomes slightly electronegative. Will have left the carboxylic group in which it originated, and now we have an ionized acidic group. Either before or even after this ionization, there is a strong affinity of the carboxyl group with the water around it. Because let's look at what happened before the ionization occurred. This carbonyl here is strongly electronegative, and therefore it will participate in hydrogen bonding to the water solvent here, i.e. this proton will be shared a bit between the oxygen of the water molecule and the oxygen right here. Similarly here, this oxygen will be slightly electronegative, as for the reasons I've just described. And here, once again, there may be some weak hydrogen bonding going on, although not as effective as over here, where we have a double bond and where we have a lot of concentration of a cloud of electrons pulled towards the oxygen atom. And this begins to give us clues as to why certain molecules are soluble in water and others are insoluble. For example, if we look at aliphatic compounds, let's look at a compound that's structured like this. I guess most people would call this pentane, and we can call it that too. And this has no electronegativity or positivity by virtue of the equal affinities of these two kinds of atoms, that is the hydrogens and the carbons, for electrons. And as a consequence, this will not be able to form any hydrogen bonds with the solvent around it if the solvent happens to be water. So there's not good bonding here. And this will, in fact, also, if one puts this in a solution of water, this will cause all the water molecules to line up in a certain way, to almost a quasi-crystal, around the aliphatic molecule. They'll be ordered in a certain layer around the aliphatic molecule without being able to form any strong hydrogen bonds with them. And this ordering represents a loss of chaos, a loss of entropy. Entropy is chaos, it's disorder, it's what happens, let's say, at 10:55 when we all leave the room, all of a sudden order becomes chaotic. And here, before this lining up occurred, the water molecules were chaotically arrayed throughout the solvent. After this lining up occurred, there was a loss of entropy, there was a loss of chaos, and thermodynamics tells us that generally the ordering of molecules is disfavored. And consequently, we now have two reasons why this molecule doesn't like to be in the midst of water. First of all, it's unable to form hydrogen bonds with the solvent. And second of all, there's a decrease in the entropy and the chaos that occurs when this molecule directly confronts water. And because of that, those two reasons, it turns out that this molecule doesn't like to be in the aliphatic molecule, as one would call this in organic chemistry, doesn't like to be in water. And its a dislike of water is often called its hydrophobicity, or we often call it might as well spell it right, hydrophobic, i.e. it really hates to be in water. If somebody has rabies, at one stage of rabies, almost near the terminal stage, the individual becomes hydrophobic because he or she doesn't like to drink water for reasons that are obscure, at least to me. Now, conversely, molecules that have carboxyl groups on it would be called hydrophilic. And as we'll see over this lecture and the next one, these hydrophobic and hydrophilic tendencies tend to have great effects on the overall behavior of molecules. Let's, for example, imagine a situation where we have a long aliphatic tail like this. In fact, these tails can go on in certain aliphatic compounds. They can go on for 20 or even 30 carbons. And at the end of this, let's just put arbitrarily a carboxyl group. And let's say we've ionized it. So here's an acidic group that's ionized. It's shed its proton. It's actually acquired a net negative charge. And now we have something, this molecule is a bit schizoid, because on one end of it, it loves to be in water. The other end of it hates to be in water. And this has strong effects. It's sometimes called amphipathic. And, but we don't need to worry about that word. And therefore, this carboxyl head loves to stick its head, to immerse its head in water, and these things, the aliphatic portion, hates to be in water. Now, as a consequence of these rather conflicted feelings that these molecules have about water, we can ask the question, what happens when we put such molecules actually into water? And what we see here is the following, that if we were to construct, for example, a molecule of the sort that has, here, in this case, we're talking about a molecule that has two hydrophobic tails. We'll get into its detailed structure shortly, but just imagine for a moment two long hydrophobic tails out here, ended with a hydrophilic head. And under such situations, if we put thousands of these or millions of these molecules into a solution of water, what we will then see is no pointer? All right. Pointer? All right. What we will then see is that the hydrophilic head groups, which are here depicted in red, will point their way outwards. They will want to stick their heads in water. And conversely, the hydrophobic tails, fleeing from the water, will actually associate one with the other. And so you have a structure that's called, in this case, called a micelle, where you form this little globular sphere where the lipid tails are tucked inside and therefore are actually being shielded from any direct exposure to water. This structure down here, the lipid bilayer, is actually, as we will discuss in greater detail shortly, the overall topology of the way most biological membranes are organized. In fact, virtually all of them. Why is that? Because biological membranes separate two hydrophilic or two aqueous spaces. Whenever you see a membrane indicated, Implicit in that drawing is the fact that each one of these membranes is actually a bilayer. There are never any monolayers of lipids in living cells. Each one of these vesicles you see here is actually a lipid bilayer with an aqueous inside and once again aqueous on the outside. Again, much of the thermodynamic stability that allows these vesicles to remain intact rather than just diffuse apart is created by these hydrophilic and hydrophobic forces which tie such molecules together or will rip them apart. Now, in truth, there are yet other kinds of forces that govern the affinity of molecules to one another. For example, let's imagine a situation where we have an ionized acidic group of the sort we just talked about before. Now, and by the way, here, let's say I'll draw the negative charge on one of these two oxygens, if you can see that. But the truth is that the electrons are swarming back and forth, and so the negative charge is shared equally. The net negative one electron charge is shared equally between these two oxygen atoms. And this is obviously an area of great electronegativity. Independent of that, let's imagine up here we have a basic group. Let's see an amine group over here. And the fact of the matter is amine groups, NH2 groups, that's what an amine is. Here's an amine group. This is a carboxylic group. And the amine group, which is used very often in biochemistry, it actually has an affinity. It has an unpaired set of electrons on the nitrogen, and so it likes to attract protons to it, which causes it to be called basic. And this attraction, the scavenging of protons, perhaps from the water, will obviously give this whole group here a net positive charge, a charge equal to the charge of one proton. Here, once again, we can imagine that this is hydrophilic because this charge group can once again also associate quite intimately with aqueous solvent. Now, independent of any other forces that might exist here, indeed, one could imagine situations where there is a sharing of a proton and therefore a hydrogen bond formed between these two. Independent of that is the simple electrostatic interaction of these two groups. That is the mutual attraction of positive and negative groups, one to the other. And the electrostatic interactions, you can't quantify exactly how many kilocalories per mole there is because the energetic value of an electrostatic interaction is equal to 1 over r squared, where r is the distance between these two charged groups. And obviously, the further apart you get, the weaker the attraction with one another. There are also what are called van der Waals interactions. And van der Waals interactions come from the fact that if we were to have, for example, two molecules over here, which are not normally charged in any way, let's just talk about two aliphatic chains again. And I won't put in all the protons and everything, but just imagine a situation like this. What will happen is that because of the fluctuations of electrons, because the electrons are swimming around here all the time, moving from one area to the next, they're never equally distributed homogeneously over a long period of time. There will be brief instants in time, microseconds or even nanoseconds, when there happens to be more electrons over here than right here, just by chance. And this area of unequal distribution of electrons will in turn induce the opposite kind of electron shift in a neighboring molecule down here, obviously depending on the distance between them. But the negative here will repel electrons down here. The positive here will attract electrons down here. And so you will have these two quasi-polar arrangements here and here, very ephemeral, that is lasting for a very short transient period of time, but nonetheless sufficient to give a very weak interaction between these two molecules, which may persist only for a microsecond and then be dissipated because the charge is then redistributed once again. And as a consequence of that, one has very weak interactions, which in the great scheme of things play only a very minor role in the overall energy which holds molecules together.